Hello everyone, I'm Yaldin from University of Toronto. Today I'm going to talk about our work, intra-operator scheduler for CNN acceleration. This is a joint work with collaborators from University of Toronto, Victor Institute, MIT and CMU. Our work starts from observing that the sequential execution widely adopted by deep learning frameworks underutilizes the hardware. In this work, we propose intra-operator scheduler that uses the intra-operator parallelization to improve the device utilization and accelerate the CNN execution. Inside iOS, we employ dynamic programming algorithm to explore the schedule space exhaustively and find the optimal schedule. iOS achieves 1.1 to 1.5 times speedup comparing to state-of-the-art libraries. CNN models are widely used in our daily life. It is important to efficiently deploy these models. However, is CNN inference in current deep learning libraries while utilizing the underlying hardware? The answer is no. First, let's look at the trend in CNN design. Here we use VGNet, Inception V3, and NASNet as examples. People tend to use more convolutions in their network. However, the average size of convolution decreased. On the other hand, the GPU peak performance increased a lot. We take NVIDIA Tesla GPUs as an example. The peak performance increases almost linearly with the time. Then let's have a look at the intra- and inter-operator parallelization. Sequential execution is widely adopted by deep learning frameworks, which execute the operators one by one. Computation of the operator is parallelized through the threads in a GPU kernel. We call such kind of parallelization intra-operator parallelization. It can suffer from underutilization problem, especially when we execute a small operator on a powerful GPU. On the other hand, we can do the computation of multiple operators simultaneously. We call this kind of parallelization as intra-operator parallelization, which usually has a better device utilization. We use a concrete example to show this. In this example, the utilization of operator B is 33%, while the utilization of concurrent execution of operator A and B is 71%. There are different ways to group operators to do the inter-operator parallelization. Let's first look at an existing approach, wavefront schedule policy. Wavefront schedule policy executes all available operators stage by stage. We use this model to illustrate this schedule policy. At the beginning of execution, there are three convolutions ready to execute: convolution A, C, and D. Wavefront policy would choose the three convolutions here as the first stage. After that, we can execute convolution B because its dependent convolution A has been executed in the first stage. The latency of this schedule is 0.37 milliseconds. However, if we move the convolution C from the first stage to the second stage, we can get a better schedule, which takes 0.33 milliseconds. There are two reasons of the speedup. First, we can only get a marginal benefit when we put an operator to a stage that has already saturated the device. Second, when we put more operators to front stages, the later stage would suffer from underutilization problem due to the less operators. This gives us an example why wavefront schedule policy is suboptimal. The general idea of iOS is to explore the schedule space exhaustively. It examines all schedules and finds the best one. However, the biggest challenge of this idea is that the number of potential schedules is exponential in the number of operators. For example, the NASNet model has more than 10 to 12 schedules, which makes it prohibitive to enumerate each schedule. To address this challenge, we observe that optimal schedule for a subgraph can be reduced. We take this model as an example. There are two incomplete schedules for this model. Both of them have scheduled operator E, F, and G, and leave operators A, B, C, and D unscheduled. If we found the optimal schedule for the unscheduled subgraph, we can reuse it in the two incomplete schedules. With this observation, we propose to use dynamic programming algorithm to reuse the optimal schedule for a subgraph. However, the time complexity to schedule a general graph is still exponential in the number of vertices. When considering the problem in more depth, we found that the weight of the thin computation graph is usually small. Here, we use weights to mean the maximum number of parallelizable operators in the model. We take inception network as an example. This is the last inception block. There are 6 parallelizable operators. Therefore, the weight of the inception model is 6. With this observation, we prove that time complexity of dynamic programming algorithm of iOS is only exponential in the weight of the computation graph. Then, let's have a closer look at the dynamic programming adopted by iOS. What iOS does is to break the complicated problem that finds the optimal schedule for the whole computation graph into simpler subproblems that find the optimal schedule for subgraphs. This formula describes how this reduction works. I will explain each component in the formula through this example of computation graph. Here, S represents the operators of the computation graph we want to schedule. We'll use latency S to represent the latency of the optimal schedule for S. To find the optimal schedule, we enumerate all potential last stage S prime and convert the original problem into a subproblem that finds the optimal schedule for S minus S prime. In this progress, we need to measure the latency of last stage S prime. We can definitely have the last stage of optimal schedule enumerated. Therefore, we can find the optimal schedule through this dynamic programming algorithm. Then let's have a look at some components in this formula in more details. Let's first look at the stage latency component. This component measures the latency of parallel execution of operators in the stage S prime. iOS considers 2 parallelization strategies. Let's first look at the concurrent execution strategy. In sequential execution, operators are executed one by one on GPU. However, if the 2 operators are independent, we can concurrently execute them by launching multiple GPU kernels at the same time. This method is generally applicable because we can concurrently execute different operators. However, because the operators are usually optimized with the assumption that they can occupy the whole device, we can easily get suboptimal performance due to resource contention problem. Then let's have a look at the second strategy, operator merge. If we can find a kernel that can do the computation of all operators in the stage, we can just execute that kernel instead of launching many kernels. This is the idea of operator merge. We can use an example to illustrate this. Here, we have 2 convolutions share the same input. We can stack their filters together and get a large kernel. Operator merge is not universally applicable because we cannot always find such a kernel to do all the computation of S prime. However, it usually has a better performance because it reduces the number of kernel launches and potentially reduces memory accesses. We use usually here to indicate that sometimes it may be slower than concurrent execution. For example, we may enlarge a kernel to make it fusible with other kernels, which increases the computation. Therefore, iOS would try both strategies and select the better one. Then let's have a look at another component. How can we determine whether a stage S prime can be a last stage of S? We find that S prime can be a last stage of S if and only if there is no edges from S prime to S minus S prime. This is because we have to finish all operators before the last stage first. Let's look at this example. We want to schedule operators S. We choose 2 candidates of last stage here. All edges between S prime and S minus S prime are from S minus S prime to S prime. We also give an counterexample here. S prime prime is not a last stage of S because there is an edge from S prime prime to S minus S prime prime, which violates the dependency. Let's look at the transition graph, which describes the relationship between subproblems. Then we give the time complexity of iOS. We use this simple model to illustrate the transition graph. The graph contains all valid state S. For this example, we have 6 states, S1 to S6. The edges of the transition graph contains all edges from S to S minus S prime. For example, there is an edge from S1 to S2 when S1 S prime contains a single operator B. Here, S2 equals to S1 minus S prime. Each edge corresponds to a stage and has its latency as weight. We put all edges here. Any path from the state with all operators to the empty state corresponds to a schedule. For example, the path shown here corresponds to a schedule with 2 stages. What iOS does is to find the shortest path from among all such paths. Therefore, the time complexity of iOS is determined by the number of edges in the transition graph. We have proved that the time complexity of iOS is n over d plus 1 and all of that parts to 2d in the paper. Here, n is the number of operators, and d is the maximum number of parallelizable operators. The time complexity is only exponential in d, which is usually small for thin computation graphs. This is all about our proposed method. Let's have a look at the experiments. We take 4 diverse convolutional neural networks as benchmarks. The first 2 are Inception V3 and SwissNet, which are expert design networks. The third and fourth one are RandMore and NASNet, which are generated by neural architecture search. We compare iOS with state-of-the-art QDN-based frameworks. We also compare iOS with different schedules. All of them are compared on iOS runtime. We conduct experiments on NVIDIA TeslaView 100, and the versions of CUDA and QDN libraries are shown here. iOS takes QDN-provided kernels and use CUDA streams to concurrently execute kernels. We compare iOS with state-of-the-art QDN-based frameworks. All performance is normalized to the best framework. We compare iOS with TensorFlow, a state-of-the-art deep learning framework, and TensorFlow XLA with a compilation optimization. Tassel is a transformation-based optimizer that uses function-preserving transformations to find most efficient equivalent computation graph. TVM is a state-of-the-art deep learning compilation stack. TVM QDN is TVM backed with QDN-provided kernels. TensorRT is NVIDIA-provided high-performance inference engine. iOS outperforms all QDN-based frameworks on all benchmarks and achieves 1.1 to 1.5 times speedup. This is because all baselines suffer from underutilization problem due to sequential execution. We also compare with different schedules. For fair comparison, all schedules are compared on iOS runtime. The performance is normalized to the best schedule. Sequential schedule executes all the operators one by one according to some topological order of the computation graph. Wavefront schedule executes all available operators stage by stage. iOS merge and iOS parallel only consider a fixed parallelization strategy. iOS both consider both strategies. iOS both achieves the best performance. Here, sequential schedule suffers from underutilization problem because it only uses the intra-operator parallelization. Wavefront schedule is suboptimal because it is an unbalanced schedule. iOS merge and iOS parallel use fixed parallelization and is suboptimal. We profile active warps of different schedules and try explaining the reason of iOS speedup. We keep running the sequential schedule and iOS schedule of this simple model, and profile the active warps every 2.1 millisecond. We get the active warps per millisecond for both sequential schedule and iOS schedule. The active warps of iOS schedule is 1.58 times than the ones of sequential schedule. When we have more active warps, it's more likely that we have eligible warps to execute at each cycle, which makes iOS have higher device utilization. In conclusion, we found that sequential execution suffers from underutilization problem, especially for a small operator on a powerful GPU. We propose an intra-operator scheduler to utilize both intra and inter-operator parallelism. We employ dynamic programming algorithm to explore the schedule space exhaustively, and proves that the time complexity is only exponential in the width of the computation graph, which is usually small, making the exhaustive exploration practical. iOS achieves 1.1 to 1.5 times speedup, comparing to the state-of-the-art libraries. We have open sourced our code and welcome to check it out. Thank you.